This video is the first of a series of videos on filters and magnitudes and colors and spectral energy distributions and color magnitude diagrams. Tons of really important stuff. I've got this fairly long talk broken into chapters, and each one of them has takeaway points. I'm expecting you to have questions, so you should ask me. You're going to need to understand all of this. You're going to have questions. So keep asking questions to get it. I'm not expecting you to be able to watch all of this and understand all of it in a day. You probably will have to watch at least some of these movies more than once to get it. And if you have a better way to explain something, please share it. Let me know how I could explain it better. Now, in order to explain the very first thing about filters, I'm going to have to drop out a PowerPoint to show you something. Okay, these are filters. You may have encountered these in other contexts before. These particular ones happen to be theater gel, so they're just colored cellophane. But the effect is, if you look through the blue filter, then all you see is blue. If you look through the green filter, then all you see is green. If you look through the red filter, then all you see is red. That's the basic concept of astronomical filters as well. So let's see if we can explore this a little bit more. Here I have a bracelet that has a bunch of rainbow beads. And if I get the lighting right, you can see that there's red, orange, yellow, green, blue, purple, right? So now let's see what happens when I put the red filter on. So the red is at the top over here. And you can see that the red beads look bright. The red and yellow and orange look bright. But green and later look pretty black until you get down to the purple, where it's a little bit brighter, right? Because if you think of it, there's some red that's part of purple light. So now let's try green. So here, the green cellophane, the green filter is just not as good. But you can see that the green beads are among the brightest in this stack. Now, if I look through blue, now it's the red end up here that looks black. And the blues are the ones that look brighter. So that's the basic idea, even with astronomical images. If you have an image that you take in blue, the things that will be bright are the things that are blue. If you take an image in red, the things that will be bright are the things that are red. If you take an image in green, the things that you see through that are green will be bright. Okay, so this is a sad and pathetic PowerPoint version of the demo that I just did. PowerPoint doesn't handle filters too well, but I found this picture online of a red truck underneath a rainbow. And within the confines of PowerPoint, I'm going to put a red filter in front. And you see, it just doesn't work as well as the cellophane in the demo we just did. But the idea is that it's only letting red light through. So here's sort of another step towards quantifying this understanding of filters. So I've got a schematic plot here of transmission as a function of wavelength. And ideally, an idealized filter, which doesn't actually exist in real life, but an idealized red filter would only let light in that's red. So nothing blue, nothing green, nothing yellow, nothing orange. When it gets to red, it slams up and abruptly starts allowing through any and all red photons. And then when it gets done with the red, it abruptly turns off and lets none of the magenta through. So that's the idealized version of a filter. And mathematically, this is called a top hat function because it looks like a top hat. But this is more reality. That before was more of a cartoon. This is reality. So here I've got relative transmission as a function of wavelength. So this is a real R-band filter from Kit Peak. And you can see that it lets no light in until about 5,500 angstroms. And then it slams on pretty quick, right? But it's not an infinite slope. There's a finite slope to this. And then look, it's not straight all the way across. And it has attenuated. There's no place where 100% of the light gets through. It attenuates something at every wavelength, and it attenuates different wavelengths at a slightly different amount. And then it turns off pretty abruptly. But look, it's got this long red tail. So it's not a top hat function, but it's trying. It's trying to get there. So there's always light loss when you put the light through a filter. And it's got some structure to it that could affect the measurements that you make. So the simplest way to understand that is if I have an imaginary source that puts out a lot of energy at 8,000 angstroms, but not so much at 7,000, then that red leak, that red tail, is going to result in a measurement of brightness for that source that is brighter than you might expect because of that red leak. Here's a lot more example filter band passes. So here again, we have transmission as a function of wavelength, this time in nanometers. And so the clear filter might be easiest to understand. It cuts on at around 300 nanometers and then tries to let all of the light in to some wavelength longer than what's shown here on this plot, right? So then we have R filters, right? So we've got a Sloan R filter, which is closer to a top hat function than the previous one. And this is a more really not at all top hat function, right? There's another R filter, and it's not top hat at all. It's got a lot of long tail to it. So if you have, again, something that's really bright at 800 nanometers or 8,000 angstroms, that's going to affect the R measurement you make of that source. We've got a U filter and a B filter. You see that U and B, even at their best, are only letting through about 60% of the light. We've got a Sloan G filter, which again is trying really hard to be a top hat function. We've got a V filter here in green, which is not doing a good job of being a top hat filter. There's I, which is pretty good, and Sloan Z, which is pretty good too. Then we've got some narrowband filters in there. We've got an H alpha filter and an O3 filter. So those, the filters that let lots of light through, those are broadband filters. The filters that let only a tiny bit of light through, those are narrowband filters. And this is allowing through only light corresponding to the H alpha transition. If the light is redshifted out of that band, it's not going to help. But it's only letting in wavelengths around a narrow range around the H alpha filter. This is an oxygen 3 forbidden line. You find a lot of those in star forming regions. And so this is a filter that is often used for that. But there again, it's centered on the not redshifted wavelength of oxygen 3. So this is a picture of the actual filters on the camera for Sloan. And the way that the Sloan Digital Sky Survey worked is it has, you see, arrays of filters and CCDs underneath, and it had something called drift scanning, right, where it would point and it would let the sky move across the field of view at the same rate at which the charges were being transferred through the CCDs. So you'd end up with stripes, right? So stripes going up and more or less up and down in this view, and so you get the same star in 5 colors. Here's another view of the filters that you might get of these same bands, but more for a telescope. So we've got G band here, it's labeled G because it's supposed to be greenish, but it sure looks blue to me. Then there's Z, which is near infrared, just looks black to us because we don't see infrared. There's U band, which is closer to the ultraviolet. Again, we don't see through that. I band is a deep red, and R, surprisingly, even though R is red, that to me looks like, when you see it up close and live and in person, it looks like construction vest orange, right? It's a really intense orange. So the names of the filters are meant to identify the filters, and the mnemonics that you might come up with, like, oh, G is green, isn't going to help you when it comes to reality, but it is going to help you remember in terms of where in the spectrum it falls. In other words, U being ultraviolet is the bluest, G is in the middle, and Z is in the near infrared. So now moving further into the near infrared, here we've got transmission as a function of wavelength. And the black is the atmospheric transmission. So you can see there's a lot of bumps and wiggles in here. And that's because the atmosphere has lots of handy molecules in it, like water and oxygen and carbon dioxide and carbon monoxide. And all of those molecules take bites out of the spectrum in the near infrared. So not all the near infrared gets to the ground, but it does so in windows. So the J-band filter is designed to line up with this atmospheric window, H-band with this window, and K with this window. So I don't remember what all the structure, which molecules are which in here, but this deep absorption is water. And so the original K-band definition extended further to the red. But because water is so variable in our atmosphere, it made it really hard to calibrate and trust K magnitudes. So these are all 2-mass filters, and 2-mass use something called K-short. The idea being that it's cut off the long wavelengths, so then you don't have to worry quite so much about variable humidity from night to night, or even over the course of a night. You can still get reliable K-band measurements. These are the 4 WISE bands. Again, in this case, it's not transmission, it's response, but basically the same concept as a function of wavelength, this time in microns. So we've got WISE 1, WISE 2, WISE 3, and WISE 4. So look, they are all attenuating light. This is very much not a top hat function. It's pretty steeply angled. This one is pretty close to a top hat function. This one is very broad, and this one is not at all a top hat function again. So here the names are coming either from the channel names, like WISE 1, 2, 3, and 4, or the effective wavelengths, like 3.5 microns is the effective wavelength, the weighted wavelength of this filter, 4.5 microns, or 4.6 microns rather. This one is 12 microns, and this one is 22 microns. Now, a lot of people, when they look at WISE 1 being 3.4 microns and IRAC 1 being 3.6 microns, they think, oh, it's close. And WISE 2 and IRAC 2 are 4.6 and 4.5 microns. I think, oh, it's the same. It's not. The blue is the WISE filter. The gray underneath it is the IRAC 1 filter. So you see it's very different. And WISE 2 and IRAC 2 are different. IRAC 3 and IRAC 4 don't really have any WISE counterparts, although part of IRAC 4 overlaps with the WISE 3 band. And again, WISE 4 being 22 microns and MIPS 24 being 24 microns, people think, oh, they're the same, but they're not, because the filter transmission is different. And so the measurements that you make through these filters are different. So in terms of filter names, there are different filters or even filter systems that have been used over the course of time. Initially, it was photographic plates, and so you had an effective filter of everything the light went through to get to you. So the atmosphere, the telescope, mirrors, lenses if it had it, or reflection off of mirrors. Then it goes through the filters, which you can effectively think of as like that slabs of colored plastic or glass, like the theater gels from earlier. You can also have more sophisticated filters that are going to be very different as a function of wavelength. For example, radio filters look like, it can look like screens, right? Or a grid of metal, because for radio, the wavelengths are very long. And so the filters have to block out long wavelengths. There are systems. So there's a Johnson system, which is one of the oldest filter systems that are UBVRI, all in caps. More recently, the R and I filters are different. So those are Cousins filters. So those are the most commonly used Johnson system, is the Johnson-Cousins system. So it's Johnson UBV and R sub C for Cousins and I sub C for Cousins I. And those are just better to work with. The R and I from Cousins are easier and better to work with than Johnson. Optical bands most often have a letter name. So when you write capital U, it's not the same thing as little u. Capital I is not the same as little I. It's not just me being sloppy. When I talk about GRIZY or UGRIZ filters, those are really the names. You can also sometimes have primes. So R prime, I prime, that means kind of like Sloan R and kind of like Sloan I, but really not. And H alpha is a narrowband filter. So GRIZY is Pan-STARRS, RIH alpha is IFAS, UGRIZ is Sloan, and 2-mass K is technically K short, but people do get sloppy about that. Sometimes they just say K without the subscript. IR bands most often have a number, which is sometimes a channel number, sometimes it's a wavelength, but it doesn't have a letter name like the optical systems do. The filters, of course, do have finite width to them. In other words, there's a range of wavelengths allowed, but they are often represented as an effective wavelength of the filter. So that's just a weighted average of the filter plus transmission, and that's the wavelength at which we place the point when we're making an SED. So even though, say, IRAC 1 allows more light in than just 3.6 microns, we plot the IRAC point at 3.6 microns when we put it on, say, an SED. So the effective wavelengths here for Ys, actually I think this is a typo, it should be 3.4 microns for Ys 1, 4.6 microns for Ys 2, 12 for Ys 3, and 22 for Ys 4. IRAC and MIPS are 3.6, 4.5, 5.8, 8, and 24. So you can see that the effective wavelength is inexorably blended with the filter transmission. So if you want, and depending on the context, you may wish to represent a photometric point with an error bar on the x-axis to demonstrate the range of wavelengths included. So here we have something that is, is not exactly just a plain spectrum. It's relative altitude and scale heights. This comes from an exoplanet paper where they're studying exoplanet atmospheres. The details of that are less important than looking at how they're showing this. So we've got a whole bunch of spectra here, and then we've got IRAC 1 and 2 points shown here. So you see they've placed the point at 3.6 microns, but they've added an x-axis error bar to indicate that the light contributing to this point is actually coming from a broader range of wavelengths. So in this case, the data have IRAC 1 and 2 at about the same. We have IRAC 2 brighter, 2 brighter, 1 brighter, 1 brighter, 2 brighter, 2 brighter, 2 brighter. You see it's telling you things about the constituents of this atmosphere. But I just wanted to show this as an example of plotting a photometric point with a finite X error bar. In the context of an SED, this doesn't really matter because look at the very small range of wavelengths shown on this plot. When we make an SED plot, we're going to have a very much larger range of wavelengths, and so it's not going to matter if you want to plot the x-axis error bar to indicate the range of wavelengths. It's probably going to be smaller than the point that you're using. So just I have a couple slides that are an aside in terms of other things that might make filter transmission curves make more sense. So for graphic designers, exact color matching is super important. So there are machines out there that allow you to measure the brightness of a color as a function of wavelength. Technically, this is reflection and not transmission. Transmission is like a filter, and this is reflection, but still. And they're plotting power versus wavelength. Okay, not quite the same thing, but the concept is similar. Look, so what they did, they took this machine, and he took an entire box of Crayola crayons and stuffed it into the machine. So we've got white that turns on and is pretty bright all the way across. We've got the red family of points, which are pretty low in the blue and then come up in the red, except for this guy, which is more of a purple. Carnation pink is what it's called. It's got a contribution in blue and then a contribution in red. The green family turns on and then turns off again, like this guy here. And then the blue family has much more blue wavelengths and then tends to turn off when you get to the red, except for the purples, right? You've got some blue contribution and then some red contribution. Here we have another one of these commercially available tools. This one happens to be from someone who at the time was working for the International Dark Sky Association. And so they had bought this tool specifically to try to measure the brightness as a function of wavelength so that they could show how some of these LED lights are different from or better than the compressed sodium lights, the pressurized sodium lights. So we've got intensity again as a function of wavelength. And of course, when he got this tool, he was running around taking measurements of everything he could find. And this is an orange lava lamp. So very little purple, very little blue, very little green, more yellow, more red and orange, and it falls off when you get to the magenta. Now here's what he actually bought the tool for, is looking for the sodium lamp, the low pressure sodium lamp versus the LEDs. And so here he was demonstrating that indeed the narrow band amber LED is quite comparable to the low pressure sodium lamp. So in terms of light pollution, it's better to use in terms of light pollution, it doesn't matter, but in terms of energy usage, it's better to use the LEDs. And if you can replace them, not with broadband LEDs, but with these kind of LEDs, you don't have the light pollution that comes from some of these the more broadband lights. So the main point to take away from this filter discussion is that filters block all but a range of wavelengths from reaching the detector. A relatively narrow range of wavelengths compared to what we can see by eye. but broad compared to a single emission line. You can have broadband filters, you can have narrowband filters. We're going to be mostly working with the broadband filters. The filter names vary. Sometimes they're letters, sometimes they're channels or numbers corresponding to the wavelengths. Filters have effective wavelengths, which is what we associate with the brightness measurement through that filter. So when we go to plot them on an SED, we take the brightness measured through that filter and the effective wavelength of the filter, and we plot them at that location in an SED.